All right, welcome everyone to our defense today. So before I start introducing Greg, let me give you a few information about how the way this is going to work. So we have about 1 hour for this defense. So all participants will be muted throughout the defense. So, and also please do not attempt to turn on your video or share your screen during the talk. So at the end of the presentation, there would be an opportunity for the audience to ask questions. And also, if you want to say anything nice about Greg, it's going to be your time. And I'd like to introduce Greg Bongey, a little bit about his bio. He received his undergrad degree at Beloit College in Wisconsin, and he had received a major in geology and a minor in biology. And earlier on, he was interested in paleontology. I see that he first started pursuing his interest in marine science when he was studying abroad in the Fiji in 2010. But he was very much interested in marine science since his early age because he watched a movie on kelp forests at the age of 4. After college, he completed a GeoCorps internship at Bryce Canyon National Park, and taught English at Henan University. I'm sure I'm saying that wrong, in China.
Oh, pretty close, actually. Yeah.
Let's see. Between 2013 and 2014, worked as a substitute teacher in Las Vegas, mainly in elementary school in 2015. Then he joined Moss Landing. Originally, his research interest was in developing a subtitled research project examining the impact of sediment scar on rocky bottom benthic invertebrates in California kelp forests. That didn't work really well, so he switched to a very different type of research, which has to do with the clay minerals, as you'll learn today, and using our brand new instrument, X-ray diffractometer, which has been fixed right now next door to the SEM room where I am today. While he was at Moss Landing, he took several jobs. He was a naturalist at Camp Sea Lab, different summers. He works as a benthic invertebrate technician at USGS, gave tours for middle school at Point Lobos, and in particular, TA'd for me GeoOsh in 2015 and 2017. I'm very thankful for Greg Tiaship. It was very, very helpful. And he also volunteered at the Monterey Aquarium for 3 years. And he got the red jacket and everything, which I don't know what it means, but I'm sure it's a big honor. While he was at Moss Landing, he acted as student body treasurer in 2016. And most importantly, he was in a puppet show, in a open house, in the cast first in 2016. Then he became a writer and finally led lead writer, co-director, and cast in 2018. That was a huge career in puppeteering. He also obtained a few awards at MLML, Lowry Family Marine Science Outreach Scholarship in 2020, and the Lundstrom Memorial Scholarship in 2018. So I'm very excited for Greg's defense today on the relationship between weathering and climate variability in the high relief tropical region during the ice ages. Those are the results from IODP Expedition 363 offshore record of Papua New Guinea. Greg, it's all yours.
All right. Thank you so much, Ivano, for that introduction. And thank you, everyone, for coming to my thesis defense. I'm going to turn off my video so you can focus entirely on the PowerPoint in front of you. So today I'm going to be telling you about how I used clay mineral records to examine the relationships between weathering and climate variability in a very high relief tropical environment, that being the island of Papua New Guinea, well, the country of Papua New Guinea. And I used, as Ivano mentioned, sediment cores from the International Ocean Discovery Project, Expedition 363. All right, introduction. I'll first start off by telling you about chemical weathering and its relationship with carbon dioxide in the atmosphere before moving on to introduce clay minerals. After that, I'll tell you about my study site in Papua New Guinea and then move on to my thesis questions. So the Earth's climate is very closely coupled with atmospheric carbon dioxide, or CO2. And CO2 in the atmosphere is modulated by numerous different processes happening on multiple different different timescales. These include oceanographic, biological, physical, chemical, and geological processes. And my thesis focused on trying to better understand the process of the weathering of terrestrial rock and how it relates to the carbon cycle, particularly as it occurs in the tropics. There are two kinds of weathering. And by the way, I should also add that weathering of rock is a process that works on timescales of thousands to hundreds of thousands of years. So this is much more long-term modification of CO2 levels than things like photosynthesis. So there are two kinds of weathering that I'll talk about today, mechanical and chemical weathering. With mechanical weathering, this happens when you have rock in a cool, dry environment. Water percolates into the interstitial space within the rock, and when it freezes into ice, it expands, exerting pressure, breaking and fragmenting the rock into smaller and smaller pieces as this repeatedly occurs. But the rock is not chemically altered in any way. With chemical weathering, this happens when rock is in a hot, wet, humid environment. When water percolates into these rocks, an acidic reaction occurs in which the minerals in the rock are actually chemically altered. And as a result of this, the rock is broken down into both soluble and insoluble byproducts. And chemical weathering is by far the largest source of weathering on the planet, and is also the type of weathering that pulls carbon dioxide out of the atmosphere. And the way it does this is carbon dioxide and rainwater combine in the atmosphere to form carbonic acid. This carbonic acid then rains down to the Earth's surface, where it can interact with minerals, unstable minerals, such as this potassium feldspar. And this acidic reaction leaches the soluble components out from the potassium feldspar, leaving behind the silicate skeleton, which we know of as clay. And as a result of this process, the carbon dioxide that was originally in the atmosphere becomes locked up in bicarbonate. And all of these components from the reaction, including bicarbonate, then flow down to the ocean, and the bicarbonate can then be sequestered in the form of shells of marine organisms, removing that CO2 from the atmosphere. So the more weathering you have, the more clays you have produced, and the more carbon dioxide is removed from the atmospheric system. And since the clay minerals are the only physical byproduct of this reaction, they can be used to examine weathering mechanisms in the past. So what is a clay mineral? Clay minerals are sheet-like silicates that are composed of two main building blocks. First, there is the tetrahedral unit, which is a silicon or aluminum atom surrounded by 4 oxygens. Then there is the octahedral unit, which is composed of aluminum, magnesium, or iron with oxygen or OH ions around it. And these two units both extend into sheets, which stack atop each other. And I want you to think of this sequence of sheets as sandwiches or burgers. And all of these clay particles stack on top of each other because it's such a sheet-like clay. And every unique species of clay mineral has its own specific sequence of these layers and also its own elemental composition. You can think of it as different seasonings within the sandwich. For instance, brucite is one specific type of octahedral layer that is rich in magnesium. There are 4 main groups of clay minerals. Chlorite is by far the thickest, fattest, most complex of the clay minerals. It is produced from felsic minerals that make up the continental crust. And it is produced from mechanical weathering, which again is what happens when you have cold, dry climates, typical of mountains and high latitudes. There's no chemical alteration, the rock breaks, and chlorite is what comes out. Illite is similar to chlorite in that it also originates from the same kind of material, felsic minerals that make up the continental crust, but it is the product of chemical weathering. In this case, the brucite layer that is forming the double-decker stack of chlorite has been degraded down into a simple layer of kaolinite. And as a result, illite is a thinner clay particle, only 10 angstroms thick rather than 14. And illite can weather from chlorite. So these two clay minerals are very frequently associated with one another. Illite forms under the typical terrestrial weathering conditions, namely river systems, making it the most widespread clay on the continents. Smectite also originates from chemical weathering, but it comes from a different source material. It originates from mafic minerals that make up the oceanic crust. So you can think of it as having a different seasoning, a different elemental composition. And because it originates from oceanic material, it is most common in volcanic island systems and in open ocean environments. Finally, we have kaolinite, which is the most stripped down, basic, simple clay molecule, only 7 angstroms thick. And the only place where you can really form kaolinite is where you have very intensive chemical weathering conditions, typical of hot, wet, humid environments that we find in the tropics. And it is produced from other clays that have been sitting in those conditions for extended periods of time. So because every clay mineral has its own specific environment in which it is formed, we can use clay minerals as indicators of weathering conditions. This map shows the most abundant clay mineral in the clay size fraction of seafloor sediments. And you will see, as we might expect, chlorite is the most abundant clay in cold environments. Illite is most abundant in areas where we have major river systems entering the ocean. Smectite is most abundant in open ocean basins and next to volcanic island systems. And kaolinite is most abundant in hot, wet areas. So clays are just one part of the sediment entering the ocean, and we're interested in chemical weathering. So let's look at where chemical weathering in general is highest. So this map shows the sediment yield across the planet. Those are represented in the different colors. Sediment yield is tons per square kilometer per year of sediment produced in each region. But I want you to focus more on the different arrows emanating from the different regions. These arrows represent sediment discharge in millions of tons per year. And draw your eyes particularly toward this one very fat arrow coming from the Indonesian archipelago. Sediment production in this area is extremely high. This map shows the arrows coming from the different islands in this system. The reason for this is twofold. First, there's tectonics. So the Australian plate is moving northward at an extremely rapid pace of 3 centimeters per year. And as this is happening, the northern plates are subducting underneath the Australian plate. In the case of New Guinea, islands on the Pacific plate are actually accreting on to the leading margin of the Australian continent. And as a result of this process, there's very rapid mountain building occurring in this area. And this rapid mountain building is what has caused the formation of all of the volcanic islands that make up the Indonesian archipelago. These are very young islands, 3 to 5 million years of age, and they're extremely mountainous, so much so that we actually have glaciers right next to the equator. And all of this tectonic activity is happening right in the warmest body of water on the planet, the Western Pacific the warmest body of seawater on the planet. And because of this massive body of warm water, there's very high precipitation. It's always raining right here. And this combination of tectonics and oceanography means that chemical weathering rates in this region are massive. And this massive chemical weathering has happened very recently, pulling down carbon dioxide from the atmosphere only at a level that was not happening 3 or 5 million years ago. And as such, it is thought to have helped trigger the ice ages. And weathering rates are particularly high in the island of New Guinea. To give you a sense of scale, the island of New Guinea produces the same annual volume of sediment as the entire continent of North America, making this an important region in terms of the Earth's carbon cycle. Within this region, the Sepik River is the largest sediment contributor. So this makes it an ideal study site for examining changes in clay mineral weathering. First of all, because this is a really important area in terms of sediment production and therefore CO2 drawdown. And also because this region has been evolving so quickly that sediment records from this location can actually display how the weathering processes have changed across the development of the region and across the different ice ages. So let me introduce Papua New Guinea. So I made a little map here to make this easier to describe the main topographic features of the area. There are 2 main mountain systems. First, there is the New Guinea Highlands, which forms the spine of the island. The New Guinea Highlands are made up of continental crust. Then there are numerous coastal volcanic mountain ranges made up of oceanic crust material. And between these two mountain systems, there is the Sepik Basin, through which there are two major rivers that flow. First of all is the Sepik River, which is the largest river on the island in terms of volume, and the Ramu River. These two rivers have very proximal river mouths that are constantly emitting these huge plumes of sediment that you can see here. So my study was using seafloor sediment records with sediments from these rivers. And for the rest of the talk, I'm going to be referring to it as the Sepik system, but what I'm really referring to is the output from both the Sepik and the Ramu rivers. All right, so the samples that I looked at, the sediment records that I looked at were collected by the International Ocean Discovery Program, Expedition 363. IODP is the shorthand for this program. IODP sends its research vessel around the world where it deploys its drill rig to collect seafloor sediment cores, which look like this once they're brought up on board. And these marine sediment cores can be analyzed in numerous different ways. And I used records from two sites for my study, 1484 and 1485. These are both on the continental slope of Papua New Guinea's northern coastline, and they are down current of the Sepik system for much of the year due to the New Guinea countercurrent. These sediment records have already been analyzed in terms of grain size by Aiello et al. 2019. This is showing the dominant sediment grain size texture. So more pelagic, finer material is down here on the legend. And these are some pictures displaying the different sediment types, with the gray, white, and black representing the percentages of clay, silt, and sand, respectively. So the 1484 record goes back to about 300,000 years. The 1485 record goes back a little more than 500,000 years. And the ages for these sediments were determined using the isotopic signature of nanofossils, particularly benthic foraminifera. So these records provide documentation of changes in oceanographic conditions over time. We can see quite clearly here that the depositional environment has changed from the oldest to the youngest samples. And this has been proposed to reflect changes in the Sepik River Basin. So we don't yet know what the clay minerals will reveal, and that is the focus of my study. So my first question is, what is the regional clay assemblage of the Sepik system? We have many clay mineral records from Southeast Asia and the islands to the western part of the Indonesian archipelago, but we have very few clay records from New Guinea, despite its major potential importance in the carbon cycle. So this is a major gap in the region, and one of the main goals of this study is to help put the weathering system of this region into context. I hypothesized that the Sepik system's clay assemblage will resemble that of Borneo, right here in the middle of the archipelago. Both Borneo and Papua New Guinea are massive islands with highly mountainous terrain, and they are also both composed mainly of continental crust. There are some differences between the two islands. Borneo has more extensive lowlands, and New Guinea is more tectonically active, unlike Borneo. My second question is, what long-term changes occur in the Sepik system's clay mineral record? How have things changed from the oldest to the youngest samples? So the sediment records show that there are finer materials in the older samples, more mud and silt and more biogenic material. And this has been attributed to the evolution of the Sepik Basin, with the region hypothesized to be what we call a successor basin. So let me explain what this means. So here is a sequence of maps showing a hypothetical model on how the Sepik system evolved based on Aiello et al. 2019. And based on the oldest sediments, which are mostly pelagic sediments, mud and silt, and later some biogenic ooze, mainly coccoliths, we know that this was a pelagic system 550,000 years ago, meaning that sites 1484 and 1485 were much further offshore than they are today. As the region evolved and the coastal volcanic mountain ranges uplifted, this shallow sea was enclosed into an embayment. This bay gradually filled up with sediments eroding off of the two mountain systems. And we can test this successor basin model using clay minerals. So I hypothesized that the younger samples will have more chlorite and illite, because those are the more terrestrial clays that we'd expect in this situation. And the younger samples will have less smectite because this is much less pelagic than at the beginning of the record. My third question was, what glacial scale changes occur during the SEPIC system's clay mineral record? So this record spans multiple different ice ages, and we can see how weathering responds to that. The traditional understanding of glacial weathering is that when you have an ice age, you have cooler, drier conditions on the planet, which means that you have less chemical weathering overall. And the consequence for this in terms of the carbon cycle would be that if you have less chemical weathering during the ice ages, you have less CO2 being removed from the atmosphere. This would mean that the planet would start to warm again and the glacial conditions would be reversed, making this a negative feedback loop. There has recently been evidence, however, for a very alternative hypothesis of glacial weathering by Wan et al. 2017, based on a study in the South China Sea. Wan et al. 2017 pointed out that in the tropics, where most chemical weathering occurs, the temperature is always going to be pretty hot. It's always going to be pretty humid and wet. So weathering conditions might not actually change that much in the tropics, whether it's a glacial or not. However, during an ice age, sea level will be lower, exposing a broader area of terrain for that intensive chemical weathering. So if this was the case, you would actually have more chemical weathering during an ice age. And this would mean you have more CO2 being pulled out of the atmosphere. The planet would start to cool even more, and glacial weathering conditions, glacial conditions would be intensified, making this a positive feedback loop. So it is important for understanding the weathering relationship to the Earth's carbon cycle to determine how broadly applicable Wan et al.'s findings are to other regions of the tropics. And New Guinea is a very high relief area in contrast to Wan et al.'s study site. I hypothesized that the observations by Wan et al. Would hold true in New Guinea, and that as a result, we'd have more chemical weathering expressed through higher amounts of kaolite during glaciations. All right, moving on to my methodology. I'll first talk about my sampling strategy and then my sample preparation techniques. I'll then introduce to you the science of X-ray diffraction, followed by the additional analyses I did to turn that X-ray diffraction data into clay mineral data. Now, before I tell you about my sample selection strategy, I need to introduce this image, which shows a record of delta oxygen 18 isotopes as they have changed throughout the past 600,000 years. And this delta oxygen 18 record comes from benthic foraminifera from across the world. So delta oxygen 18 is a proxy for ice volume and therefore for sea level. Lower down on the curve represents higher global ice volume and lower mean sea level. And the delta oxygen 18 curve has been the basis for delineating interglacial conditions, shown in pink, from glacial conditions, shown in white. You will notice that the glacial cycles are not symmetrical. The planet tends to cool gradually, followed by very rapid periods of warming. So these periods of rapid warming on the planet are referred to as glacial terminations, and they are characterized by rapid sea level rise, which is important for sedimentary environments. So for my sampling, I needed to make sure that in addition to getting samples from across the entire length of the record, I needed to make sure that glacials, interglacials, and glacial terminations were all represented in my sampling techniques. I also had to make sure that I compared sediments from the same depositional environment. I wanted sediments that had settled out of the water column and not sediments that reached their final location due to underwater landslides, forms of resedimentation. So to avoid resedimented sediments, I mostly sampled very fine-grained material, less than 10 microns in size. So I'm now going to show you the samples that I selected overlaying on the delta oxygen 18 curve for the two sites. Remember, 1484 is not as old of a record as 1485. I had a total of 124 samples between the two sites with an average sampling interval of every 6,000 to 9,000 years. So to process these samples, I needed to remove all the non-clay components in order to analyze the clay composition. So to start out, I had 2 acid bath treatments. First was acetic acid in order to dissolve the carbonates in the samples. And this was done for a week or more, followed by hydrogen peroxide in order to remove organic material in the sediments. This was done for 3 to 5 weeks. Afterwards, I had to separate the sediments based on grain size. To do this, I used a centrifuge. After spinning in the centrifuge, the sediments stratified into different layers with the finer material, the clays, on top, which I could then decant and use to make my slides. For the slide preparation, I needed my clay particles to be oriented in the same way, parallel to the slide. I didn't want to have randomly oriented clay particles. So to achieve this, I put the decanted clays into a vessel connected to a vacuum pump. At the bottom of the vessel was a filter, and the pressure from the vacuum sucked the water through the holes in the filter and pulled the clay particles against the filter. And that would leave me with an aggregate of oriented clay particles at the bottom, which I could then transfer from the filter to the glass slide. So to measure these clays, I used an X-ray diffractometer to assess the clay minerals on the glass slides. Now, this is a brand new machine that the Moss Landing Marine Lab just recently acquired. My thesis was the first to use it. So we had a lot of trial and error figuring out how it works. Ultimately, there are 2 main components of the machine. There is an X-ray generator, which shoots a beam of X-rays at the clay sample. And this is done individually, one slide at a time. And then there is an X-ray detector, which measures X-rays that have been diffracted off of the atoms in that sample. And both of these components change angle relative to the sample. And the wonderful thing about X-rays, the reason we use X-rays specifically for this kind of study, is that the wavelength of X-rays is actually shorter than the spacing between 2 planes of atoms within a mineral. We call this spacing the D spacing. And because the wavelength is shorter, that means that when these 2 components change angle, the X-rays will actually respond in different ways to the atoms within the mineral, which we can record based on what the detector is sensing. At most angles, we have what is called destructive interference. In this situation, the detector is reading a very low number of diffracted X-rays, because when the X-rays from the beam respond to the sample, the diffracted X-rays are in opposition to each other, in which the troughs and the peaks are not aligned. And when this happens, the X-rays cancel each other out, leading to destructive interference, and the detector doesn't measure very much. However, at very specific angles, the X-rays that are diffracted from the atoms will actually be in phase with each other, causing them to build, which we call constructive interference. So here it's showing destructive interference is occurring for the majority of this diffractogram. This diffractogram is showing the angle of the 2 components of the machine on the x-axis and the intensity of measured X-rays on the y-axis. So for most of this diffractogram, the detector recorded very low readings, but at specific angles, constructive interference occurred, rendering as peaks. And the relationship between the angles that occur and the spacing between the atomic planes is basically a function of trigonometry. We can convert the angle at which constructive interference occurs to the D spacing between atomic planes. And this principle is referred to as Bragg's law. So since every clay mineral has its own unique crystal lattice, it will produce its own unique sequence of diffraction peaks. And I can use this to identify the different clay minerals in the sample. However, there are some complications here in that multiple clays share peaks in specific locations, which can make it difficult to distinguish them from another when you have a diffractogram such as mine, where you have lots of clays mixed together, and it's hard to determine which peaks belong to which clays. There are some techniques around this, however. For instance, smectite and chlorite both share a peak at 6 degrees 2 theta. However, we can resolve this. Smectite is more commonly known as kitty litter. Kitty litter works the way it does because smectite is an expanding clay. It has a layer of OH ions, which can accommodate organic molecules, causing them to expand. So after running all my slides on the XRD the first time, I put them in a glycolating chamber, a pot with glycol at the bottom, and steamed it. And that ethylene glycol steam was then absorbed into any smectites present in the sample. This caused the despacing to expand, changing the angle at which constructive interference occurs, and thus changing the position of the peak, allowing me to differentiate smectite from chlorite. So I ran every slide at least twice, untreated and glycolated. Now, the relative heights between the peaks in a diffractogram cannot actually be used to quantify clay percentages. To do that, the traditional method has been to recreate diffractograms by making clay mixes. That is, you actually mix powders of pure clay together, and you just do this until you have produced a clay slide that yields the same diffractogram as your sample. This is not practical if you have very complex clay mineral assemblages or if you have lots of different samples like I did. So I use the more modern method, which is enabled by all the past work that's been done. Essentially, I'm still creating clay mixes and seeing which ones match, but I'm doing it on a computer, making computer simulations of clay mixes. I used a program called NewMod, in which I controlled the different conditions input into the machines, into the computer. I input the different clay species present in my model and the molecular conditions for those clays. And based on the inputs, the program would then simulate what a diffractogram would look like using the theories of crystallography and the known despacings for these different components that I input. And then I would just adjust these inputs until I have a match. So this is a screenshot from NewMod showing showing one of my experimental data files, an actual diffractogram from one of my samples. Using NewMod, I am now simulating pure illite. I have now added to that simulation percentages of all 4 clay components. And I just keep doing that until I have an equivalent match, a rough match between the simulation and my actual sample. And this is assumed to be a good approximation of the sample's composition. Now, it's possible to have multiple different solutions that will yield matching diffractograms. So I ran every sample in NewMod twice using 2 different solutions, using 2 different types of criteria, peak height versus line shape. And then I took the average composition between these 2 solutions. All right, moving on to my results. I'll first talk about the average clay composition for both sites, and then I'll talk about how the clay records have changed over time. All right, so I did a total of 548 scans on the XRD based on the numerous different treatments I did of the multiple samples, or samples from the multiple sites. And in general, most scans took approximately half an hour to run. Okay, so the clay mineral assemblage. All 4 clay species were present at both sites. Illite and chlorite dominated the assemblage with approximately 40% of each clay mineral. There were also lower amounts of kaolinite and smectite, approximately 10% each. And the average clay assemblages of both sites were very similar to each other, which perhaps isn't surprising given their close proximity. So how has it changed over time? I'm going to break down this graph piece by piece. This first component is the delta oxygen 18 curve, which again is a proxy for ice volume and sea level, lower being higher ice volume and lower sea level. This shows the delta oxygen 18 curve from the 1484 and 1485 sediment records. This was measured using benthic foraminifera within these sediment cores, and the delta oxygen 18 readings were what was utilized in order to assign the ages to the samples, as published in Aiello et al. So here are the clay mineral records. You can see that these are highly variable, very noisy records. So it's very beneficial for making any judgment of them to overlay some additional features onto this graph. Before I do that, I wanted to just explain briefly. You see that there are multiple lines within each plot. These two different, all the lines are 3-point moving averages. And the line on top and the line on bottom represent different solutions for the composition of the clay from the two different solutions in new mod. And then the core line in the middle represents the average that was calculated. So that's why there's 3 lines. So we can look at this with respect to interglacials shown in pink versus glacials shown in white and see how things match up with those different intervals. We can also look at that at the clay record with respect to glacial terminations. And I found that there were more instances where the variability coincided with glacial terminations. So I'll be displaying that for the rest of my presentation. We can also overlay different features from the sediment record onto this graph. So this gray unit represents an interval of high resedimentation. That is, we had lots of underwater landslides during this part of the record. Which means that any sediment deposition recorded in these clays might be more likely to be a poorer indicator of what was actually happening with weathering at the time. So I am going to be removing the glacial terminations from this resedimented interval and from the oldest part of the record, just because that clears it up a little bit and it's less likely to be relevant. Okay, we can also overlay the graph with different kinds of sedimentation, in this case, pelagic sedimentation. The blue represents the mud and silt from the older part of the record, and the yellow represents the biogenic unit, composed mainly of coccolith ooze, which represents the most pelagic conditions of the record that have been observed. All right, so let's look at a few things we can say about this to start. Long-term trends. There are 2 apparent long-term trends with this data. Chlorite appears to increase from the oldest to the youngest samples, and illite at first glance appears to decrease from the oldest to the youngest samples. However, there is a notable shift in the abundance of clay minerals in the oldest samples, especially with illite. Illite is very high before this dotted line, but is actually fairly stable after the dotted line. And it's also worth noting that illite and chlorite actually co-vary with each other during this interval shown in yellow. So at first glance, illite and chlorite looked like they were in opposition to each other, but it actually appears as if they might actually be doing the same thing. It's just illite is very high in those oldest samples. So doing a linear regression from the dotted line onward shows that chlorite still does display an increase in abundance from the oldest to the youngest record, the oldest to the youngest samples, regardless of whether you do it from the oldest sample or from the dotted line onward. Illite is actually quite stable, on the other hand, after that shift. Okay, finally, there are 2 intervals where a specific clay, there are 2 different clay minerals that had intervals of covariance with the delta oxygen 18 curve, which could potentially suggest periods that could potentially suggest the clays being affected by changes in sea level or some other glacially controlled process. Moving on to the discussion. I'll first start off by talking about the regional clay mineral assemblage, followed by the long-term trends, and then the glacial scale variability. All right, so this is a ternary diagram. A ternary diagram is a means of plotting composition with 3 different components. Illite and chlorite are combined as one of the 3 components because they both originate from terrestrial clay sources. And this is showing right now basically what we already saw in the pie charts, that the records are dominated by illite and chlorite with lower amounts of kaolinite and illite. Kaolinite and smectite, that's a mistake. And both sites are very similar. The wonderful thing about ternary diagrams is that they make it much easier to compare different sites. So this map is showing a compilation of clay mineral records from across Southeast Asia. Each pie chart represents the clay assemblage from each region. And rather than comparing all the pie charts side by side, it's much easier to simply plot them all on the ternary diagram. And doing this, we can see immediately that northern Borneo has the closest proximity in clay mineral assemblage to the SEPIC system. So why might this be? It's worth also comparing Western and Eastern Borneo, which occur here in green on the ternary diagram. Western and Eastern Borneo have a fairly even abundance of kaolinite versus illite smectite. And they both occur in areas of Borneo with more extensive lowland terrain, where you have more hot, wet, humid conditions that can produce kaolinite. Northern Borneo, on the other hand, is much more analogous to the SEPIC system in that it is highly mountainous. So remember, mountainous conditions are where we would have high chlorite production due to the mechanical weathering and high illite production due to foothills and river systems coming down from this region. So Borneo, at least in the northern part of the island, is analogous to the SEPIC system in terms of its source material and mountainous terrain. So let's interpret the clay mineral record over the long term now. So the increase in chlorite from the oldest to the youngest samples, or from the shift onward, happens to correspond very well with the tectonic activity in the region. Remember that the Australian plate is constantly moving northward with constant subduction and constant mountain building. So this glacier that is shown occurs on the island of New Guinea, and the mountains that support this glacier have been getting larger and larger, those being the New Guinea highlands. And as these mountains have continued to get larger, the glaciations, subsequent ice ages, became increasingly intense. So this would mean that you'd have an increase in mechanical weathering conditions compared to the oldest part of the record, when the mountains had not built up as much. So the increase in chloride over time can be attributed to the increase in mountain building. But why is illite so high in the oldest samples? Remember that at the beginning of the record, we know it was a pelagic system. And in a pelagic system, we would expect high amounts of smectite. Illite is a riverborne clay, and there's no good mechanism for transporting such high volumes of illite, a riverborne clay, to the open ocean at this time of the sediment record. One potential explanation is that these oldest samples are the deepest sediments that were examined, both in terms of burial depth and water depth. And as a result, these samples were exposed to very high pressures. And when sediments are exposed to high pressures, this can cause them to be altered through the process of burial diagenesis. And the diagenesis of smectite to illite, that is, smectite being altered by pressure into illite, is very well documented in the world's oceans. It's one of the earliest diagenetic processes that occurs in marine sediments. So it's very possible that this high illite observed in the oldest samples is actually pelagically derived smectite that simply was altered due to the pressure of overlying strata. All right, now let's look at glacial scale variability. Again, this is a very noisy, highly variable record, so it's hard to be certain about any of these changes that we can observe, but we can pay attention to any coincidences that happen. So there are two major variations shown here with the arrows. The older of these two variations has an increase in smectite and kaolinite and a decrease in illite and chlorite. And this variation happens to coincide very well with a glacial termination. It is the fifth most recent glacial termination, so we call it termination T5. This variation also coincides with the coccolith ooze interval shown in yellow. The coccolith ooze, remember, represents the most pelagic conditions on the record. The younger of these two major variations also coincides with the glacial termination, the second most recent one, T2. and it shares the increase in smectite and the decrease in illite. There is another much smaller variation that we can't be as certain about on whether it's real, but I pointed out because it also happens to occur at a termination, T4, and it has the same exact pattern of clay mineral abundance changes as the oldest of these variations. So in trying to figure out what these variations mean, if anything, the only one that might potentially be associated with pelagic deposition is the oldest one. So let's take a look at that one first. With pelagic deposition, we would expect more smectite and less of the terrestrial-borne clays, chlorite and illite. And remember that we interpreted this high amount of illite as smectite that was diagenetically altered. So if this was the case, then perhaps this oldest variation isn't so much of a variation as it is residual smectite, just smectite that had not been altered into illite because it wasn't under quite enough pressure. So from this perspective, we can look at these three variations in terms of their relationship with the glacial terminations. The oldest of these variations has a quite small or even non-existent change in size. The termination T4 is associated with a very small variation as well. The most recent of these variations that happens at a termination is the most notable of them, which suggests that if these variations are real and if they are truly associated with glacial terminations, then the effect that the glacial termination has imparted has increased over time. Now, how exactly would this work? Glacial terminations are characterized by rapid sea level rise. And rapid sea level rise means that lowland terrain is flooded by the rising sea level. This reduces the amount of weathering surface available, and it also causes any soils in those lowland terrains to be reworked, which could create a change in the sediment that reaches the deposition site. So at the beginning of the record, when this was a shallow sea, there was much less lowland terrain available to be flooded by rising sea levels during glacial terminations. However, after the Sepik Basin evolved and you have all this lowland terrain that makes up the Sepik River system, changes in sea level during glacial terminations might have been much more significant, allowing for more soil reworking and allowing for this larger shift that you only see, so the larger variation that you only see in the most recent of these terminations. Now I want to discuss the kaolinite-illite ratio. Kaolinite and illite are both chemically weathered clays, but kaolinite represents much more intensive chemical weathering than illite does. So a higher ratio between kaolinite and illite indicates more intensive chemical weathering overall. So the reason I'm focusing on kaolinite-illite ratio is because this was the basis for Wan et al.'s hypothesis in 2017. Remember, their hypothesis was based on the observation that in the South China Sea, the kaolinite-illite ratio increased during the ice ages. So this is their data at the bottom of this graph, and I'm showing a fat pink line to make it easier to see the overall trend. And you can see that the kaolinite-illite ratio is higher during glacials, shown in white, than it is in interglacials, shown in gray. And based on this, Wan et al. Argued that in the tropics, sea level change exposes greater areas for chemical weathering, and as a result, you have higher chemical weathering during the ice ages. So what is my thesis finding? Do I have any evidence of that here in the much more topographically high relief site of New Guinea? And what we find is that there actually is a change in the Ki ratio, but only in the most recent samples. You can see that kaolinite-illite ratio is higher in the white glacials than it is in the gray interglacials. So once again, this goes back to the change in lowland terrain over time. At the beginning of the record, the there was not very much lowland terrain to be exposed to rising sea levels. And it also means that when sea levels go down, there's not much change either. But after the Sepik Basin evolved, drops in sea level associated with ice ages would have exposed much more lowland terrain than earlier in the record. So this suggests that the increase of chemical weathering during ice ages explained by Wan et al., identified by Wan et al., can actually occur in high relief tropical environments such as New Guinea, provided you have lowland terrain available. Conclusions. My first question was, what is the regional clay assemblage of the Sepik system? And I hypothesized that it would be similar to Borneo. And this turned out to be correct. The clay composition was most similar to northern Borneo. Both the Sepik system and northern Borneo were dominated by illite and chlorite, and this reflects the mountainous environment of both locations and the continental crust that makes up these mountains. My second question was, what long-term changes occur in the Sepik system's clay mineral record? And I hypothesized that younger samples will have more chlorite and illite and less smectite. This turned out to be true for chlorite, although we didn't find any evidence of this for illite. And this also turned out to be true for smectite, assuming that my diagenesis explanation is correct. So you can see the overall trends over the long term right here. Most clays were very stable throughout the record, although chlorite was the exception. It increased over time as we attributed to the uplift, the ongoing uplift of the New Guinea highlands. Illite was high only in the very oldest samples and was fairly stable onward from that. But we attribute this to have been high smectite originally associated with pelagic conditions. And this high smectite simply was diagenetically altered into illite due to overlying pressure. Finally, what glacial scale changes occur in the Sepik system's clay mineral record? I hypothesized that kaolinite would increase during glaciations. And this was not the case. It turns out to be much more complex than that. We didn't find any strong evidence of variation that reflects changes in ice ages versus interglacials in terms of total clay abundances. Of the variations in the clay percentages that were observed, the older variation was attributed to pelagic deposition. As you can see, it is associated with the coccolith ooze interval and is the last pelagic sediment that survives after diagenesis. And the younger variation was attributed mainly to reworking of soils from sea level rise associated with glacial terminations. And these later terminations would have had more of an impact on clay mineral assemblages because later on in the Sepik system's evolution, you have more lowland terrain available susceptible to sea level rise, which you simply did not have at the beginning of this time. So finally, the kaolinite-illite ratio was highest in glacial times rather than in interglacial times, but we only found evidence in the most recent part of the record. And the fact that it only occurred in the most recent part of the record when lowland terrain is available after the evolution of the Sepik Basin suggests that the model by Wan et al. For tropical weathering increasing during ice ages can hold true in very high relief environments such as New Guinea, provided you have lowland terrain punctuating that highly mountainous region. So with that, I would like to thank you very much for attending my thesis defense. I would like to thank a lot of different people. First of all, I would like to thank Ivano Aiello, my advisor. Thank you so much for taking me into the lab and for always being there to troubleshoot the machine and for caring so much about me as a student. Thank you so much to Maxime Grand and Anna Cristina Ravello for being on my thesis committee. I really appreciate it. You guys definitely have sharp eyes and caught lots of little things that definitely made my paper a better one. and had some very keen insight as well as to other things I should acknowledge. I also really want to thank Scott Hamilton and Diana Steller. They both provided me with a lot of guidance on my original thesis project idea, and their classes were so amazing. The most rewarding part of my program has been the classes that I took with you guys. So thank you so much. I also wanted to thank MLML facilities, particularly Chris Machado, for helping me troubleshoot the furnace that I used for heat treatments that I did not describe in this presentation. I'd like to thank the Geological Oceanography Lab for helping me rehearse my presentation and for sharing the geology lab with me. I'd like to thank my funding sources. And then mostly of all, I really want to thank my family. The last 6 years have been such a challenge, and I never would have gotten through it without the love from you guys. So thank you from Mom and Dad. You've always been so loving and caring. Thank you to my wacky siblings, Lee, Jay, and Brian. I love you guys. And thank you so much to Safari. She has been my loving partner throughout my whole time at Moss Landing, and I never would have been able to get through this without her. So thank you so much. I will now take any questions you guys may have.
All right. That was wonderful. Thank you so much, Greg. You look like a very weathered feldspar.
Yeah. So I did not have time to talk about the scanning electron microscope component of my thesis, but I was very proud of this picture. It shows 2 feldspars. One's very weathered, one is not.
And like many other students, Greg discovered that you can't fit everything in one presentation.
Yeah.
I'd like to open up to questions, as Greg said. I can start with the first one since I'm talking, and which is kind of a classic question. Where would you go after this? I mean, how would you? So you have 3 questions, you have 3 hypotheses.
Sorry, I can't. So do you see the question, or am I?
No, I'm saying, where would you take the study next?
Oh, I suppose expanding it to other locations. I mean, the one et al. Hypothesis is a complete reversal of the traditional way we understand how weathering changes in glacial cycles. So seeing if it can be exported to other areas is important. There's a lot of variability at precessional scales that we were not able to do with this study. So my study was looking at ice ages, how it occurs, how weathering changes across the ice ages, but there's not actually that much evidence for changes in precipitation in response to the ice ages. Most of the changes in precipitation in the tropics come, at least in the Indonesian archipelago, comes from changes in the Earth's precession, that is the Earth's alignment, the wobble of the Earth. So we would ideally have been able to sample at very fine timescales, like these are 20,000 year cycles, much shorter than what we were able to examine with this study. And seeing how clay minerals change on those short precessional timescales would be a very useful thing for understanding chemical weathering in the region.
Yeah, and definitely what you're showing is that so the idea of one et al. Is that you as you said, you still have wetness and rain and warmth during glacials at low altitudes. However, when you drop sea level, you're exposing more land to weathering. Mm-hmm. So you're actually, sinking more carbon, so that can enhance low stands and glacial conditions. But what you're showing is that in the Seepeak system, this might have occurred only after the Seepeak plain developed. So mm-hmm. That's good. Okay, but I want to leave it open to other. So thank you for your answers, Greg. Do we have any other question? You can also chat them. Any question for Greg? It's your chance to ask him anything you want.
Okay, I think I'm here. It's Max. I just want to, first of all, it was a fantastic defense, Greg. I mean, I really enjoyed it, and I very much appreciate, the time you took to take us through that very complex data set of yours. And I very much appreciated all the symbols you had, because I always forget, which one is elite, smectite, and all that. So very good job on that.
That was like my big, I need to make this easier to remember.
Yeah, and you did a wonderful job for all of us that are not geologists and don't play with clays all the time. I had one question with regards to that, smectite to elite diagenesis you talk about in the earlier part of your record here, on that slide here. And so you if I understand correctly, you interpret this as, as chemical diagenesis due to increased pressures, towards the bottom of your cores, pretty much, the conversion of that smectite into elite. Mm-hmm. So that must be something that has been seen in pretty much all the cores that have been analyzed for clay composition that are older than about 400,000 years or so, right? Or
the complicated thing about it is that there's a lot of different factors that control. So it's the overlying sediments, there's temperature, there's fluid chemistry, there's the depth at which the sediments were deposited. There is definitely a way to calculate what we would expect to be the threshold at which diagenesis occurs. And that would have been a really cool thing to do for this study, but we just weren't, there were so many different components, we weren't able to do that. I don't know if it was based on information that we lacked, or if it was just a follow-up component that would have been good to analyze. But yeah, that would definitely be a good way to support that argument, if we can calculate within this particular sediment record what the expected threshold for diagenesis would be.
Okay, so this has not been seen in other records that are
similar. Oh, it has been observed in other records.
Okay.
Yeah, it's well documented in the ocean that smectite can diagenetically alter into elite. But within this region, I don't know specifically if there's records of it, but it's definitely a process that is known to occur.
I see. I had another question as well, a quick one with regards to that one hypothesis, which is very exciting indeed. So, and if I understand correctly, it states that during glacial times, you just have, a higher surface area of slope that's exposed pretty much, right? So that means that you need to consider the slope of the continental shelf in those calculations, right? Because the higher the slope, the smaller.
There tends to be a weathering profile on where different types of weathering occurs. So lowland terrain, there's a margin where you have mostly kaolinitic conditions, and then you can also have a margin where you have smectite conditions if you have the right kind of source rock available. And then, and this varies based on the source rock as well as the climate, of course. So yeah, it'd be interesting to have records from different spots actually across the land of the Sepik Basin. These are all marine sediment cores, which are not always if we actually had sediment records from within the Sepik River system and the soils, and that would definitely help support some of these arguments as well.
Okay, great. Well, thank you, Greg.
And also a quick communication. So actually the committee is gonna talk to you for a few minutes after one of these. Okay, Greg?
Okay, sure.
Do we have any other question for Greg? Yeah, one thing I want to say, Max, I mean, Greg's response was on the spot. So the sedimentation rates here are crazy. So you get to 1 meter per 1,000 years, approximately, which is that right? Or am I talking about?
I don't remember exactly what it is, but it's really high.
So it's, no, because I'm working on the Guaymas Basin now, and I'm like, I forgot which side is which, but what I'm trying to say is that you get very young sediments buried very rapidly. So that emphasizes some of those early diagenetic reactions that include the smectite to elite transitions, which is actually one of the early diagenetic products in many marine sediments. So that's what Greg said, essentially. And the Port water chemistry also shows it supports the idea. I mean, there's more evidence for that as well. Any question on kelp or subtidal ecology for Greg? It's very versatile. All right. Well, then.
Hey, Ivano, I have a question.
Oh.
Sorry, I was just having trouble unmuting.
Oh, no, you're not.
Okay. I'll just have a quick question. Thanks, Greg, for that presentation. It was great. And your thesis was also super clear and everything. So I just want to congratulate you on your ability to communicate these complex things and for your hard work. So it was really, really nice. I just have it occurs to me that what you're saying here is that there's a positive feedback, right? You're describing a positive feedback and that's that's what's novel here. And you're kind of, you know, potentially validating the existence of this positive feedback. But it seems like it changes, right, through the record. So do you think that that's just a particular thing about this location that you're looking at because of the tectonics and the development of the terrain, or do you think that there's actually a global effect?
Well, I think for this specific situation, since we have no evidence of the relationship with the Ki ratio with glacials or interglacials for the majority of the record, but we do at the same time that we have the lowland terrain of the Pacific Basin. In this situation, it is a topography thing, but I don't think there's very many records from other parts of the world, and because this observation has only been made in 2017, and what would really be good is to have records of this from lots of other places that also have lowland terrain to see if it shows up, if this process shows up in other similar locations. But
isn't it possible that, I don't know, but I'm just wondering if it's possible that even if it's, let's say the record is a reflection of some local evolution of the basins and the terrain, right? But it could still have a global effect, because at the beginning you talked about the importance of this river system, you know, globally, how large it is on a global scale. So, you know, is it possible that local tectonics and local terrain evolution could actually have a global effect if you know, it just because it's really, really fresh material, you know, that just quantitatively is globally significant, even if it's
no, absolutely. Like, even if for the rest of the world, changes in weathering in ice ages versus interglacials doesn't change much. I think it's definitely possible that if there's major changes in one part of the world, then that can have an outsized impact. Like with just using an example from paleontology, totally different world, totally different project, but at the end of the Cretaceous period, there was the Deccan Traps in India, where you just had this one location where there's tons of volcanic activity, and paleontologists are arguing over whether that the dinosaurs were already on their way to extinction from the rapid climate change from this one very localized location, or if it was exclusively the asteroid. So this is just another example of that for that particular world that I happen to be familiar with. There's definitely situations where local tectonics and local geology can make effects that affect the whole world's climate. And for this particular situation in sedimentology, I could definitely see that being possible, that local tectonic changes here in the Indonesian archipelago have a greater influence on the changes in chemical weathering than other parts of the world would. I'm not sure if I'm answering your question.
Yeah, if you look at the CO2 record for the last 800,000 years, right? It's really like each cycle is a little different, but also the amplitude of the variability changes, right? So there's some reason for why the strength of positive or negative feedbacks changed, And so that's what it reminded me of when I saw your things. Oh, is this somehow, can you somehow link this to the character of the Vostok, CO2 record? Is it, I don't know if you've thought about that, but it just occurred to me when you were giving your talk that might be some like an interesting thing to do.
Yeah, that would probably be another good follow-up analysis.
Thank you for that. Yeah, the big fat arrow you showed, Greg. I mean, that's a huge amount of sediments being delivered from the Pacific system to the world's ocean, as much as all this coming from North America. So at some point, that arrows start working, right? That's what Christine is saying. At some point, you know, that system became relevant to global biogeochemistry. And so it will be interesting to see whether there's a signal, a global signal for it.
Yeah, when that arrow becomes important.
Yeah.
There we go.
Plus, the Pacific system has been identified as a potential source for iron fertilizing primary productivity in East Equatorial Pacific. So that's another potential connection to global climate and biochemistry. Okay. So let's see, is 13 minutes past the hour. If there are no other questions, I'd like to thank everyone for joining us, especially Greg's family, and I thank everyone. And the committee will stay with Greg for a few more minutes. So thank you all again, and thank you, Greg, for the wonderful presentation.
All right, thank you so much for coming, everyone. I really appreciate it.
So let's wait for people to disconnect.